Welcome everybody. Today I'm recording in a new place, so I apologize if there's any weird microphone issues. I'm not the best editor. What I wanted to look at today is the equation sheet for a standard E&M course. This is the first half of the course, and it's a good way to study because if you know where these equations will be used, you should be able to do pretty well on the exam. If you can explain the equation, tell me where it comes from, and list out some problems where it could be used, you should do fairly well in an exam. So this is kind of how I study. And what we're going to do is just look at this entire equation and break apart each thing. So we can see over here is a ton of physical constants which are given to us. Each of them has units, each of them has a name. Let's actually go through these first and take a look at what we got going on here. So over here we have E, which is the charge of the electron, 1.6 times 10 to the negative 19. C stands for coulombs, the standard unit for electric charge. We also have, actually that's it, just the charge of the electron. We also have some masses over here. So the mass of the proton, mass of the neutron, mass of the electron. All of them are written in scientific notation and all of them in units of kilograms, which is the standard unit for mass. Over here at the top, we have Avogadro's number. So Avogadro's number is this big number, 6.02 times 10 to the 23 particles per mole. So what this is saying is you need this number of particles to create 1 mole of something. Normally you see this word mole used in a chemistry class, and standard problems that could use this number are, let's say we have 1 mole of electrons. How many electrons is that? 1 mole. Well, this is 1, and it's telling you 1 mole has this number, Avogadro's number of particles in it. And this works for anything. You could have Avogadro's number of atoms, Avogadro's number of billiard balls, whatever it is, that creates 1 mole. It's like a new definition of a number of particles. So this is given to you here. Normally it's actually written A subscript N for Avogadro's number. Don't worry about it. If a problem asks you for Avogadro's number, it should tell you that it is N in the physical constants. This over here is the speed of light. They use the letter C, and it is written with units meters per second. It is about 3 times 10 to the 8. I can't really think of a problem that would use this unless you're trying to find electrons going the speed of light or something like that. We'll see once we get to the equations. Maybe in the circuit equations, actually, they will use this. Then we have Ke, which is the constant, Coulomb's constant. Normally, it is written like this, 1 over 4 pi epsilon naught. And epsilon naught is also given to you. It's right here. They just write it differently. Either it could be this squiggly epsilon or it could be this epsilon. It is the same thing. And they also give you units for this. So you can see 1 divided by 4 and pi. These things are unitless. This thing has units, but it's 1 over this unit. So if you flip these, you should get Newton meters squared per Coulomb squared, and this equals the units for the Coulomb constant, which is actually given to you here. So you can either use this in an equation where you want to simplify. Let's say you have these constants and you want to simplify all of them for this. You could use this equation. Or if you need to actually plug in Coulomb constant to get a number, you have Newton meters squared per Coulomb squared here, and the actual value, 9 times 10 to the 9. And then we have epsilon naught. I think this is permittivity of free space or permeability. Whichever one it is, this is the other one, permittivity and permeability. This one normally you don't use until you get into the magnetic section, but they give it to you here in case you need to use it. So it has units of Tesla, I think meter per amp, if I'm not mistaken. But normally a first half course in E&M, you don't look at the magnetic field, so you don't really need to use this guy. Then they give you this conversion over here. 1 Tesla is equal to 10 to the 4 G. I'll be honest with you, I don't know what G is, and it's not going to be too useful for this course, for this part of the course either, unless I'm making a mistake. And finally, after all the masses that I talked about, you have this conversion here, which tells you 1 electron volt, which is a unit of energy, is equal to this many joules. Joules is the standard unit of energy that we use in classical mechanics courses. The electron volt is something that is used for E&M courses. So they give you this conversion here because normally electron volts is something you get from the electric potential section. Here we can write this potential in terms of volts, right? And here we have potential energy. So if we multiply this Q over here, this is the charge of the electron. We could have QV, which will give you electron volts, and that gives you energy in joules or electron volts. So that is all the physical constants here. I hope that made sense. We're going to start off all of this kind of summary here from the first section, which is the electric field. So let me actually give a big overview. So this is the electric field and force. This from the book that we've been looking at is chapter 22. Actually, this section here is from chapter 23, and so is Gauss's law. Gauss's law is from chapter 23. Chapter 22 has the standard electric field. This over here for electric potential is chapter 24. And then we get into the capacitor and circuit stuff. So I think capacitors is chapter 25, and then resistance, Ohm's law, all this stuff is chapter 26. And then at the end over here we have Kirchhoff loop rules. I'll just write it as Kirchhoff like that. I don't know which chapter this is. I haven't looked at the book that far just yet. I believe it should be chapter 26. And I think this section on RC circuits, RC stands for resistor capacitor circuits. This should also be chapter 26. So all these chapters here and the physical constants. So if you can explain each of these bubbles, you know, you have bubble 1, 2, this is actually 1, 2, 3, 4, 5, and 6. If you can explain all of these and you have a good grasp of each of them, you should be good for the test. And I would say normally this bubble here, Gauss's law, and this are the most kind of difficult sections, which is what I tried to focus most of my videos on. These things on capacitors, resistivity, and the circuits, they are still fairly difficult, but I've noticed, you know, most of the time when students study this, these 3 chapters here, 1, 2, 3, are a bit easier than these 3 chapters. So, all right, let's get started very quick to take a look at what we are going to learn. And again, this is not like a full study guide of everything. It's just kind of going over the equations and you know, getting an idea of what each equation is saying. So we're going to start off over here with the electric field. Then I'll move on to Gauss law. And then I'll move on to chapter 24, electric potential. And then the capacitors, and then resistivity, and then we'll finish off with these circuits here. Sounds good? Cool. All right, let's peep this. Let me just grab a drink of coffee. We're gonna start off with these equations here. So, what we have here, let me zoom in. First equation we have is electric field equals force with an E over here divided by Q with a 0. This is the very first equation. In the book, the very first equation you actually learn about is this one over here, which is Coulomb's law. So I'll write this over here. Coulomb's law. And what this is telling you is if you have 2 charges, let's say they are positive charges, or let's say one is negative and one is positive, or let's say 2 are negative, these guys feel a force. So opposites push each other away, they repel, negative and negative, and like charges attract each other. So Just knowing this, like kind of this little picture here, and that opposites attract but like charges repel, this will give you an idea of the direction of the force. These lines that I draw are lines of force. You can write this here. From Newton's third law, every action has an equal and opposite reaction. So this particle is pushing this particle this way, this particle is pushing this particle this way, and the force is equal and opposite. What I mean by opposite is this one is facing this direction. It has a certain magnitude, which you can calculate with this equation. It will create an equal and opposite force on this one. So this force is facing the opposite way. You can think about it as 180 degrees pointing in the opposite direction, and it is an equal force. Same thing here. These two are equal, and they're facing in opposite directions like this. Not opposite in this way, but they're facing in counter directions. Same thing here. So this Coulomb's law will actually tell you how to calculate the force between these guys. So first thing you have to know is there is a line like this conjoining the two particles. In this case, it is this line and this line. The force will always be directed on this line, along this line here. And that is actually denoted by this little r hat here. It's not included in this Coulomb law equation because this, as you see here, is not a vector. This E is a vector. It's bold with a line on top. This F is a vector. It's bold with a line on top. This E and this E are also vectors. This A, which we will get to, is also a vector. However, this F is not a vector. It is just a magnitude. And basically, it just tells you the force between these two particles. It doesn't tell you anything about the direction. So you have to know two things when working with this law. First of all, what this law means. You have the two charges here, right? This could be Q1, Q2. They have units of coulombs, and this R is the distance separating them, the length of this dashed line. This is R. So you take R, you square it, you put it down here, you multiply on the top by the actual magnitude of these charges, you multiply by KE, and if you remember, KE, if we go down to the constants, has these units, Newton meter squared per Coulomb squared. So if you plug in all the units in this equation, Newton meter squared per Coulomb squared, then we multiply by C and we multiply by C for the two charges, and we divide by meters squared for the radius. We get these two coulombs cancel with these meters cancel with these, and what we are left with is newtons, which is the force for, or the unit for force. So yeah, that is good to know. They also give you KE right here, which you can plug in if you want. And yeah, that is the first equation that you learn in the class. Then they tell you, okay, this is actually a force. You can draw it like this. Coulomb's law, capital and bold F, denoting a vector, with a subscript E because it is talking about the electric field force. Then they define this new quantity, the electric field, and they're basically telling you, what is this thing? It is the same thing as the force, which we have here, divided by a unit charge. So let's say in this scenario, we have two charges, two charges, two charges. For the force, we have two charges. If we divide out one of these and just remove them, or divide out one of these, or divide out one of these, this equation here for the electric field is basically asking you, what is the electric field at this point, P, created by these charged particles? And the equation looks like this. It's very similar to this equation, except it only has one Q. What is this Q? The Q that is creating the electric field, the charge. And in this scenario, since we have a bold vector, on this side we also have something that is bold, and it is also a vector. So what this is telling you is the direction that the electric field is pointing. This is another thing they don't show you in all the equations here. It's that the negative charges have the electric field pointing into them, like this, radially in all directions, while the positive charges emit the electric field. So it is pointing out in all directions. And that is this R here. So if you have a positive Q, like this case, you will have positive Q, this thing will be positive, this thing will be positive, this thing will be positive. So the entire magnitude will be positive, and this r hat is basically telling you the vector of the electric field is pointing along this radial direction of the charged particle, so radially, and the magnitude of this vector is 1. So this is the magnitude, 1 of the r hat vector. You multiply by this and you get the magnitude of the electric field at whatever point r. So r could be this point here, maybe this is r, or it could be this point here, maybe this is r, or it could be all the way there. You can use any distance of r to find the electric field strength at any point along or around a point charge. So this is the electric field of a point charge. This is the force between two charged particles, Q1 and Q2. This is Ke, a constant, which you can just plug into this equation. And this is an interesting equation which uses Newton's second law. So I'm going to write this over here onto the side. If you remember, Newton's second law is the force acting on an object is equal to the mass of that object multiplied by that object's acceleration. Now, what we learned was that we have Fe here. It is a new kind of force, a force due to the electric field. And if we multiply this Q over here, we get the force due to the force from an electric field or charged particles is equal to a charged particle. We can put a 0 here. This just means a unit charged particle, but it could be anything. What I mean by unit is, if you look over here at the physical constants, this is the charge of the electron. This number over here is not a unit. It is not a number 1. It is 1.6 times 10 to the negative 19. Sorry, my apologies. A unit charge would be just 1 coulomb, 1 coulomb. Just like how a unit of time would be 1 second or maybe 1 minute. It won't be 1.6 times 10 to the negative 19 minutes or seconds. A unit of distance could be 1 meter. It's not going to be 1.6 times 10 to the 19 meters. It could also be 1 kilometer. Unit just means 1. Okay? So that is what that Q with a 0 underneath it. It is just this. But this equation works if this is also not a unit. So I'm going to remove this little thing, and I'm just going to multiply this Q onto this side. So I have force of the electric field is equal to Q times E. This equation is not written over here, but you can get it from over here if you just multiply this Q on this side. And it is a very important equation. Why is it important? Because we can take this force and plug it into Newton's second law, and we get this. QE, I'm going to put a vector, is equal to MA. Okay? And this is an interesting equation because it's telling you, let me actually write it out like this. A charge, Q, it could be an electron, it could be 1 coulomb, it could be any charge, inside an electric field, whatever the electric field is, it could be anything. This charge will have this mass M. And because it is placed in an electric field, it feels a force, right? It feels a force due to the electric field, and that will create an acceleration due to Newton's second law. So that's what this here is telling you. If you want to find the acceleration due to a particle with mass M and charge Q in an electric field, you can just define this M over here, and you get this equation. A is equal to QE over M. And these are vector quantities. So you can see the acceleration is in the same direction as the electric field because these are the only things that have direction, the vector quantities. So if you want to find the acceleration due to a charged particle in an electric field with a mass M, you can just do this equation. Make sure you have all the proper units. So Q has units of coulombs, electric field has units of newtons per coulomb, and mass has units of kilograms. So we have coulombs, newtons per coulomb, coulombs cancel, newtons per kilogram will give you acceleration. And if you expand newtons, here on this equation, newtons equal kilograms meters squared, newtons equal kilograms meter per second squared. So you can write newtons like this, right? And if we have newtons per kilogram, we can replace this newtons with kilogram meter per second squared over kilogram. These kilograms cancel and you get back meters per second squared, which is the unit for acceleration. So I hope that makes sense. I'm not going to spend too much time talking about that, but I'll leave the equation there. Now, there is pretty much the completion of the equations. We have the electric field, we have the force due to charged particles. We have Ke, which is a constant inside of this. Newton's second law, along with the force due to a charged particle, gets us to this. Using this gets us to this, and we can use this equation to calculate the acceleration. Now, if you look at this equation here, it looks very similar to the equation here we have. We have a Ke over here, a Ke. We have a Q with the little I, but we'll get to the I in a second. We have an R squared. We have an I as well. And we have this R hat. So what this sum here says with the I and the I's all on these is basically telling you, hey, if you have multiple charged particles, let's say like this, and you want to find the electric field at a point over here, P, what is the electric field at this point? Well, we have charged particles here creating an electric field along each of these radial positions. Remember the line connecting the point P with each of these charged particles? So maybe this here is Q1, Q2, Q3, Q4, Q5. Each of these has a specific distance. Maybe this is R1, maybe this is R2, R3, R4, R5. If you remember, the negative charge will pull in the electric field. So it's going to create an electric field pointing along this dotted line, but it's going to be pointing towards the charge. Meanwhile, all of these are positive charges, so they're going to push away. They're going to shoot out the electric field. So if I follow this line here, I'm going to follow it. I'm going to continue following it. That means this will be the line that I draw my vector on. So I'm going to take that and basically draw this over here. I'm going to do the same with all of the other ones. We have this one here. We have this one here. And we have this final one here. All of these. And these are vectors. They are vectors of the electric field. You can call it maybe E1. Maybe this one will be E2. Maybe this one will be E3, E4, E5. And you can break apart each of these and you can calculate the magnitude of the vector using this original equation. And what this equation is telling you is, hey, just do the thing that you did over here with Ke, Q, and R squared. Ke, Q, and R squared, except replace the Q's because they're different. Here is Q1, it's negative, so you put a negative there. Here is Q2, it's different than Q1, they're not the same. Maybe this is 1 coulomb, maybe this is 2 coulombs, maybe this is 3 coulombs, maybe this is 57 coulombs, so this one is the biggest one. Maybe this is 13 coulombs, and this is a bigger one, but also smaller. A bigger charge will create a bigger electric field. A smaller charge will create a smaller electric field. So this sum is basically telling you, add up all of the contributions of the electric field due to all of these. And that's what this sum is saying. And this I simply says, okay, here we have, I labeled these with their numbers. Here we have R1 and Q1. That's what I is. We start at 1, we replace R1, we replace Q1, and our hat one here is basically telling you the direction of the electric field, which is pointing along this radial line. Radial line meaning it's on the same line as this R here. This R is this line here. This is just pointing in the same direction on this line, except it has a length of 1. And it is also including this I. And then once we're done this sum is telling you, hey, once you did 1 here, change this I to a 2. So we have R2 and Q2. I replace here 2, 2, 2. And then when we're done with that, 3. And each of these, you could just put a plus sign between them. You're basically using this equation, except here where you had 1 and 1, you do plus Ke Q2 R2 squared plus Ke Q3 R3 squared plus dot dot dot, onwards and onwards. That's what this equation is telling you. Very simple. The only thing that's not simple is actually calculating the total electric field. And this is where you need to be able to add vectors together. So how do you add these vectors together? You can't just add them together because this one is pointing in a different direction and it has a different magnitude. So how do you do that? Well, you have to know how to break apart the components of vectors. Let's say we have this, and I'm going to draw the same vectors here. Boom. This one, maybe this one here, and this one here, and there's one here. What you want to do with these guys is break them apart. So I have this, I break apart this vector into its x and y components. I do the same thing with this one. So this one is broken up into these components. And I don't have too much time to talk about components in this video, but maybe I'll do another video on breaking apart components. But you basically break apart the components of each of these vectors like that. And then you have a whole bunch of vectors here pointing in the same direction that you can add up together. And these ones you can add up together too. Search up on YouTube decomposition of vectors into their components, and you will find an example for this. So that is what this equation here is talking to you about. Then you get to chapter 23, which is this equation here. Basically what it's telling you is we have Ke. Here we have this new thing. It is called the limit. Don't worry about that too much. Basically it's saying, hey, we have a small change in Qi, and this limit goes to 0. And here you have a small change in Qi. That's the only thing different about this equation. I'll be honest with you, this equation here, you will not use. You will only use this equation. And you can see here we have E equals this new thing with the limit, but it still has the same things, Ke, Q, R squared, R hat. It even has the summation sign. The only new thing is this limit. Now, you can also see following this equation here, we have an equal sign and we have a Ke. Now we have a dq over here, R squared, R hat, and we have an integral. So this equation here, you will not use. You will use this equation. And what this equation is talking about is a continuous charge distribution. Whoops, sorry about that. So this is a continuous charge distribution. I've already done some videos of this. This is the thing that helps you find the electric field due to a charged rod. I've done some videos there at a point P. So in this case, you don't have a discrete scenario like this. These are discrete charges. You have a continuous scenario, a charged rod where each tiny piece of the rod, if I take a tiny piece, it has a small dq. That's why they called it delta qi instead of just qi in this equation. And they said the limit as this goes to 0. This is a standard way in calculus to go from discrete quantities like these to continuous quantities which use an integral like this. So this thing will help you find the electric field of this, the electric field of a ball, maybe a billiard ball of charged matter, maybe it's positively charged. You could also have a charged plane, let's say it's negatively charged, and it has some area, AB. This equation will help you do that. So that is everything that I would say about this first chapter and a little bit of the second chapter. If you know and can explain in your own words what each of these equations does, you're already going to be at a good spot because at least you'll know what the equation is used for. You know what I mean? Okay, let's move on because this video is going to be very long if I explain each equation in depth. This is just kind of a large overview. Gauss law. Gauss law is the next thing. Here are the equations for Gauss law. This says plate surface here. Sigma is surface charge density. Okay, interesting. Oh yeah, and we have these two equations here. These are actually interesting. I'll get to those in a second. So the main equation for Gauss law that I've done in my video is this equation here. You'll actually see that this equation is pretty much identical. It says phi E. This is the electric flux. That's why they use the letter phi. And they use the letter E here to tell you flux due to an electric field. And they tell you this is defined as integral surface. The integral over a surface. What is the surface? It is the Gaussian surface. We will talk about that in a second. And inside of the integral is the electric field producing the flux. dA, which is the vector defining the surface that the flux is going through, dA. And the dot product between them. So this integral, I'll be honest with you, you don't use. They actually have another way of defining it, which is this integral here with a circle in it. This is a surface integral. No need to worry about that. That's kind of a bit more of an advanced calculus topic. But you can see it's the same thing. E dot dA. Notice both of these are vector quantities because they're bold and they have a line on top of them. This is the dot product, a thing that happens between two vectors, a multiplication of two vectors, the scalar dot product. And over here, we have a new thing included, which is not included in this equation. So this equation and this equation are saying the same thing, except this second equation is a bit more useful because it includes this part. So it's telling you the electric flux is equal to the integral over the dot product of the electric field with the area vector, the normal area vector normal to the surface, and it equals the charge enclosed over epsilon naught. Cool. So I'm not going to go too deep into this because I have a whole 2-hour video on Gauss's law. Please take a look at that. I go into depth a lot, but this is pretty much the only equation you need for Gauss's law. They just show it to you here in two different ways, maybe because surface will be a bit more interesting or suggestive of you to look at instead of this little integral with a circle in it. But this is the main equation that you use. So check out my Gauss law video. I'll leave it in the link in the description below. And these two things are actually pretty interesting. They are the electric field, and here you have sigma, which they say is surface charge density. So I will mention that very quickly because I don't think this is mentioned anywhere in the book or in the equation sheet. Charged bodies have a thing called charge density. If you remember regular density, like density of water, the way you find it is you do mass over, typically it's volume, because every three-dimensional object has volume. So this is density that you learn about when you first learn about density. Density of water, you can talk about density of stainless steel is heavier or is more than the density of water. So if you drop a stainless steel ring in a pool, it's going to sink to the bottom. But the density of a basketball, for example, is less than water. So if you put a basketball in a pool, it's not going to sink to the bottom, it's going to float up. That's kind of how you learn normally about density. When you talk about electricity and magnetism or electrically charged objects, you learn about this thing called charge density. And it is literally the same definition, except here in the top where you normally had mass, you put charge and you divide it by volume. Okay? And the letter they use for volume charge density, volume charge density is this letter rho. Greek letter rho. It's like a curvy P. So I'm going to have this here, charge over volume. I hope that looks good. This is an equation that is not included in the equation sheet, but it's important to know. Now, in these problems, in classic physics problems, they like to simplify the scenario into 2D and 1D dimensions. So this is 3D. We have 2D and 1D cases because sometimes it's good to treat a problem as two-dimensional. It makes it easier to solve. It's also good to treat problems as one-dimensional. So if you have a charged rod, like a charged wire, it's very easy to solve the problem if you treat it as 1D, just a line. It becomes a little bit harder if you treat it like a three-dimensional thing with some kind of super tiny thickness with radius r. This would be a 3D rod. That complicates the problem a lot. So in physics, we like to break apart the problem into 2D and 3D cases. And in that scenario, we have new letters to define charge density. So this is surface charge density. Again, it's charge divided by area, because two-dimensional objects have only area, no volume. They are two-dimensional. You can think about a sheet of paper. Sheet of paper just has area. It has a super, super small thickness, but this thickness is negligible. Okay, and in 1D, you use the letter lambda. So this is charge over length. And this would be if you had a wire of length L and total charge Q. So this letter they use is lambda. This is, I believe, sigma. I think they write it here. Plate surface charge density. Yeah, here, this is the charge density. And here, oh no, here they use rho. Okay, I hope that is helpful for you guys. Just a quick kind of look at those things. I'll erase that and I'll keep those three charge densities. Put them here. So that is not written in the equation sheet. It might be important for you guys to write that down. That's also something that will be used here, dq, because as you see, q is used over here, and over here. So if you create a little portion of q, dq, and a portion of volume, dv, you can find rho in terms of those. So you can create an equation, dq equals rho dv. That equation will be very important to use in problems where you solve for this thing. But I would say take a look at my videos for charge distributions like the rod and see where that is used. In that problem, I just use this thing here. I use dq is equal to lambda dl for the rod. Cool. So these things here that I was going to tell you about are electric fields. And as you can see, they have a surface charge density, and they have 2 epsilon naught here, and here they have epsilon naught. These things are actual equations for the electric field of two-dimensional objects. Okay, here's the example. Example 23.8 in the textbook. Find the electric field due to an infinite plane of positive charge with a uniform surface charge density sigma. So you can take a look at how this problem is done, but basically at the end, they get that with Gauss's law, the electric field here is sigma, the surface charge density of the infinite sheet of paper, divided by 2 epsilon naught. And here, they actually ask you a what if. So they tell you, suppose 2 infinite planes of charge are parallel to each other, one positively charged and the other negatively charged. The surface charge densities of both the plates are the same magnitude. What does the electric field look like in this situation? So then they give you the answer. This is the scenario, this figure 23.18. This is the scenario that we used Gauss's law to find the answer for the electric field here. And you get electric field is equal to sigma over 2 epsilon naught. Over here, they tell you, okay, imagine we have a positive plate and a negative plate parallel to each other. It creates an electric field inside themselves like this. And what is the electric field there? Here is the answer. We first addressed this configuration in the what if section of example 23.3. The electric fields due to the 2 plates, due to the 2 planes, add in the region between the planes, resulting in a uniform field of magnitude sigma over epsilon naught. And they cancel everywhere else outside of the 2 plates to give a field of 0. Figure 23.19 shows the field lines for such a configuration. This method is a practical way to achieve uniform electric fields with finite-sized planes placed next to each other. So this is exactly what those 2 final equations tell you here. So this here is electric field due to a positively charged plate the electric field here and the electric field here equals sigma over 2 epsilon naught. While this one is if you had a positive plate and here you had a negative plate. Remember that the electric field here is shooting out of the positive one and going into the negative one. Over here outside the plate, electric field is equal to 0. Same here, electric field is equal to 0. And inside, E inside is equal to sigma over epsilon naught. So just remember, these two equations are when you use Gauss's law on a infinitely large plate like this, or two plates like that, they give you the electric field. This is for one plate, electric field here, and this is for two plates, electric field inside. On the outside, this electric field would cancel with the negative side of this electric field, and this electric field would cancel with the positive side of this electric field. That's why the external regions, we have no electric field, while the internal region, we have this electric field, which is used to have a 2. Now it's 2 times stronger, so these 2's cancel. So this gives you the sigma over epsilon naught electric field. And now we are done with everything from the first 2 chapters, and we're going to get to the electric potential. So to give you an idea, I already did a video on this, so I'm not going to spend too much time, but this is electric potential energy. This is defined in a very interesting way in the book, but it basically is equal to this. We have Q naught over here multiplied by an integral. Inside the integral, we have electric field dot product ds. So this ds is like a pathway from point A to point B, from point A to point B, right? If you multiply Q, some Q naught by the electric field, what you get is, remember the first part of the equation sheet, we get an electric force. Do you remember that equation? That is from here. Multiply this Q naught here, and you get an electric force. So what this is telling you is, we have this thing here, which is a force times a displacement, d. This gives you work, or it gives you potential energy, electric potential energy. Here they have work. So take a look at my electric potential energy video or electric potential, and you'll take a look at a deeper explanation of this. This thing has units of joules, this thing has units of newtons per coulomb, this thing normally has units of meters, and this thing has units of coulombs. You normally don't have to do this integral, but in the video where I explain electric potential, I tell you how to do this integral. And this integral is actually used a couple of times. Over here, we will get to this in a second, it is used, and over here it is used to solve for the electric potential, not electric potential energy. Over here it is used as well. Over here is a continuous charge distribution. We're going to get to these in a second, don't worry about it. So we have this definition of electric potential energy. Here you have a very similar looking equation to Coulomb's law, right? You have two charges. You have a distance on the bottom, except here it's not r squared, it's just r12, and 12 means from charge 1 to charge 2. If charge 1 is here and charge 2 is here, this is q1, this is q2. This distance here, they call it r12. So two charges multiplied on the top, ke, which is very similar to what the form of this equation looks like, Coulomb's law, except the only difference is this r squared has now changed to a singular r, not squared. So this is the potential energy between two charges. You have two charges like this. You know that they feel a force due to Coulomb's law, but what is the energy? The potential energy? This is it. You can calculate it by plugging in this number, multiplying the two charges, dividing by just the distance, and you get U, which is normally in joules. By the way, if you look at the equation sheet down here, you can convert joules into electron volts if you want and if you need to. But just know that energy has units of joules. Here, they define this new thing. This is electric potential. And they tell you, how is this defined? We take U, which is normally this, or normally this, and we divide it by Q naught. It's kind of the same thing or analogous to what we did here. We have E, it's a new definition. What is it? It is the electric field. And how is it defined? We take something that we know already, the force, and we divide it by a unit charge, Q naught. Here, we take something that we know already, the electric potential, in this case between 2 points, or in this case a general scenario, and we divide Q naught. So if you take this thing and divide Q naught, you will basically cancel this first part, and you would get this equation here. Notice how this equation and this equation are pretty much the same, except it's missing a Q naught. That's because of this definition. V is equal to U over Q naught. V is equal to U over Q naught, no Q naught. And they put these deltas here to tell you that it's a change in electric potential energy from point A to point B, a change in electric potential from point A to point B. Here, they just tell you the definition. Oh, electric potential is defined as energy over charge. This work scenario is very important. If you are given the change in electric potential and you are given a charge, so let's say the scenario with the plates. You learned that there is an electric field in here, but what you learn in this chapter is that there is a electric potential difference between these points. So if you put a charge here, this charge will move in some direction. It'll either move up or it'll move down. The way you can talk about it in classical Newtonian terms is it feels a force. Because of that force, it feels an acceleration. And because of that acceleration, you feel motion. In this energy sort of worldview, you have a charge. It is inside this new thing we've defined, which is the electric potential, and it will feel work done on it. If you remember the energy part of your physics studies, you will know that work is related to potential energy like this. Change in potential energy is equal and opposite to the change in work, the work-energy relationship. This is normally learned in a thermodynamics class or maybe a classical mechanics class once you start learning about energy. But all you have to know is you can find the work done on a charge inside an electric potential by just multiplying the thing here by charge. And what you get is volts, which is the unit of this thing here. This has units of volts. And volts are defined as joules per coulomb. How do I know this? Well, here I have energy. This has units of joules. And here I have a charge. This has units of coulombs. So 1 volt is equal to 1 joule divided by 1 coulomb. 1. This is a thing that they actually don't give you here in the equation sheet. So maybe if you want, you can add it. 1 volt is equal to 1 joule per 1 coulomb. This is an interesting thing you can add. And then you can convert joules to electron volts if you wish. Okay, cool. So, at this stage, what we're looking at is the electric potential, which is written in this equation. And what they tell you is, okay, you can go to this equation. And what this is you can pull the electric field out of this integral if the electric field is constant. If the electric field is constant over this displacement. So let's say you have 2 charged plates. You learned that the electric field here is constant everywhere. It looks like this. If you want to do this integral over this electric field, you know that the electric field is constant, E equals const. Therefore, they pull it out of the integral and put it there. And then they tell you the integral from A to B, ds, is just this thing, s. So what this is, let's say you have a path like this, right? Let me actually draw this. Let's say you have a path like this. I also talk about this in my electric potential video, but this is the path from A to B, right? From A to B. And this ds is telling you break apart this path into tiny, tiny little pieces of distance, which we call ds. They don't like using the letter d for distance because they already use the letter d in calculus for differential. So they use the letter s for distance. or path or displacement, something like this. So you take all of these, and these blue things are basically ds vectors, right? Because they have a direction. Obviously, you can see this guy's direction is different than this guy's direction, so they are vectors. Now, if you take this integral from capital A to capital B, you're basically adding all of this, and you get the total vector S. Now, in this case, it is a wonky looking path, but if you had a scenario where the path was straight, like let's say this, then you can break apart this thing into tiny little ds vectors. And if you're adding all of these up from point A to point B, that's what the integral is saying. The integral is a way of adding things up, super, super tiny things, adding up all of these ds's. Normally, these ds's should be infinitesimally small, so a length of 0, that's why the limit is used. But don't worry about that, that's a calculus thing. If you add all of these up, then what this integral is telling you is it's just the distance from here to here, which they call s. So they have this here. And because s is a vector and E is a vector, they have the dot product here. Please take a look at my electric potential video. I talk more about the dot product. So yeah, here in this, so this equation here, I'm not sure if you'll use too much. Maybe it's useful to just take a look at it, but I don't think you'll use it. This one here, you might actually use. What this is telling you is, well, take a look at this. Electric potential. You use this original equation, and they actually pull out the electric field. My bad. And in this case, the electric field is not bold anymore, and it doesn't have an arrow on it, so it's not a vector. And they also pulled it out of the integral like that. They did the same thing here. And then they're saying this from A to B is equal to D instead of S. So this is a simplification of this, except if you remember how they defined the dot product. The dot product here is, let's say, we keep this minus sign outside. Actually, let's not worry about the minus sign for now. Let's just take a look at what E dot S is. This is magnitude of E, magnitude of S, cosine of the angle between them. So this simplification here, they just relabel S into D. It's another kind of way of relabeling it. It means the exact same thing, distance or displacement, whatever, except here, cosine is equal to 1. So that means theta here, theta is equal to 0. And theta is the angle between these two vectors. So let's say this is the S vector and this is the E vector. Theta is here. In this scenario, the displacement, which is this, and the electric field vector, which is this, they are pointing in the same direction. So what this equation is telling you is it is the potential difference between two charged plates, or the potential difference in a uniform electric field. We have a uniform electric field created by charged plates like this, and it creates an electric field like this. And these plates are separated by a distance d, and inside of them they have a constant uniform electric field E. This is telling you the potential difference over here between these charged plates is literally equal to minus sign. The minus sign comes from the original equation. Electric field is the electric field inside the plates. And remember, you can find that electric field using this. This literally tells you the electric field. It's already in the equation sheet. You just have to remember that it's talking about charged plates, okay? And then you multiply this by d, the distance between the charged plates. So if you have this equation, you can, first of all, you can find the potential energy between these two plates if you put a charge in them, right? If you put a charge here and the charge is Q naught, you can find the work because you have delta V and you have Q. Here is delta V. You can calculate it like this, and they're going to give you Q. And you have delta V here. You can imagine this is delta and this is delta. You can also find the potential energy of a little charge placed in an electric field like this. So I hope that was not too speedy, quick Gonzalez. We're going to move on to the next equation just because we still have resistance and capacitors and circuits to go over. So the next thing, by the way, what this chapter is about is calculating the electric potential. The way you do it is using this equation. The dot product, the integral, and this little minus sign out front. This is the most general way of talking about change in electric potential. But you're not going to do this integral because it's kind of complicated. They actually show you a certain case where you do it here, and they show you another case here where it's for charged plates, electric potential of charged plates. If you look in the book, they also find the electric potential around a charged point. So this is what this is talking about. This is the potential, I guess, at point R, a distance r from a charge q. You can take a look. The charge over here is q, the distance r, and ke. So this thing, you can actually use this equation to find it. I already did a video on that. It's the very last video I posted. But you're not going to have to do that because this equation is given to you here. So this is the potential around a charged point, a point charge. Let's say you have it here. The potential at this point, let's call it R1, is literally equal to Ke. Let's say the charge has charge Q1 over R1. Let's say you want to find the potential at another point here, R2. The potential at this point, let's call it 2, and this is 0.1, is Ke, the same charge Q1 over R2. And now you can take these two numbers. If you subtract them, V2 minus V1, you get delta V. And now you can plug this in, or let's say you put a charge here, you can have delta V and the charge. If you multiply those two together, Q times delta V, you get the work done. If you have delta V and the charge, you can plug delta V into here and the charge, and you can find the potential energy of those two charges. It is actually given to you here as well. Cool. Also, this equation that I wrote here, delta V is equal to VA minus VB, or sometimes you see it as VB minus VA. This should have a minus sign in front of it because you flip them. So first VA VB, then VB VA, you have a minus sign. I also talk about this more in my potential energy, electric potential video. You know, if VA is bigger than VB, then VA minus VB will be positive. But if VA is smaller than VB, meaning VB is the bigger number, then this whole thing here will be negative. And if you flip them, you will spit out another negative sign here. So not too important to know that. I'm just kind of sharing it because it's what I think about when I look at these equations. And over here, you have the continuous charge distribution of the potential V. So this is the same kind of equation as this over here. You can see both of them have a Ke, both of them have a dq, and this one has an r, this one has an r squared. And also, V is not a vector, not vector. That's why you don't have this r hat here. There is no r hat. One difference though is over here you see the integral dq. Over here you don't see the integral. That's because they have a dv here. You can see this equation as dE is equal to Ke dq over r squared. And this equation just doesn't have the integral because they're saying a super small element dE is created by a super small element dq. If I take an integral, then I can replace that super small element dE with the total electric field. In this case, if I do an integral here, I could just change this to a V. Does that make sense? But since I don't have the integral, I am saying that a super small element of charge creates a super small element of the electric potential. Okay? Now finally, these last couple equations are telling you how can I find the electric field if I already have V. Okay, so let's say I have V over here. This is the potential around point charge. What these equations are telling you is if you take a derivative of V, you can see here V, if you take a derivative d dx, a derivative of this function, then you get the electric field. And you see how it's a derivative with respect to x? It gives you the x component. Here, this is a full derivative. Over here, you have the same thing except with these squiggly derivatives. These are called partial derivatives. Basically, they're telling you, take a derivative of this function v, and you'll get back the electric field for the x direction. If you do the derivative in terms of y, you will get back the electric field in the y direction. If you take the derivative in terms of z, you'll get the electric field in the z direction. Here, they have d dr. So take the derivative with respect to r. So let's actually do that to this equation very quickly. I have v, which is a function of r, is equal to ke q over r. That is exactly what I have here. Now let's say I want to find the electric field. I can use this equation over here, and I will say E subscript r. They just tell you r because, well, the electric field is a function of r, and it's pointing radially away. This is, again, telling you the potential of a point charge. So you have a point charge, it has charge q. The electric field is shooting out in all directions like this. And you actually have the electric field in the first chapter here, this. If you have the potential, which is given to you over here, you can take a derivative of this function with respect to r, and you should get the electric field. So let's do that. I'm going to rewrite electric field here. I'm going to do a minus sign. I'm going to do d dr. And then here, I will plug in v of r, right? Because I'm taking the derivative of this thing. So I'm going to do ke q r. Okay? Here, I can see that ke and q, they are constants. So I can pull them out of the derivative. They're not going to be affected by the derivative. I'm going to replace the derivative right here, and I'm going to replace everything else inside the function there. If you guys remember, the derivative of 1 over r is the same thing as, let me rewrite this here, the derivative of r to the minus 1. And now you can just do, if you've done calculus, the exponent rule. So I'm going to bring down this minus 1, ke q. I'm going to bring down this minus 1, and then I'm going to do r. Minus 1 is minus 2. And if I rewrite this minus 1 cancels with this minus 1. So I have plus, and I have keq. And then r to the minus 1 is r squared. So this is keq r squared. And if you take a look, that is the same electric field as this, keq over r squared. And we know it's in the radial direction, so we can put that r hat if we want. That is the radial direction here. You also know that just by this first chapter here. So this is not too important. I don't think you're going to be doing a problem with this. It's just telling you that if you find the change in the electric potential, remember that's what the derivative is saying. The change in, here it's saying the change in, partial derivative is a derivative, the change in. Basically, the change in the electric potential is the electric field. Okay, it's kind of like, one thing that we also haven't talked about is equipotential surfaces, but I will do another video on that. So those are all the equations in this section here, and that completes the electric potential. So the next thing I will do is capacitors, resistance, and these last couple of things, circuits, and we will get to that in just a second. So now the section on capacitors and dielectrics, I'm going to go through these equations quite quickly, and I'm going to do specific problems in a separate video. This video here, I just want to look over the equations themselves and see what they mean. So we have a capacitor, which is a element in a circuit. It looks like this. It has units of farads, and this is the circuit element. It's two equal sized bars, one next to each other. So the capacitance in a capacitor is defined as the charge Q on the capacitor divided by the potential difference over or across that capacitor. So in circuits, typically you could take a voltmeter and measure the potential difference across some circuit. This will give you this delta V, which is the same thing as the potential in the electric potential section, except in this case, it's treated a little differently. We're not looking at energy of a charge or work of a charge or motion of a charge in some electric potential. We're not looking at electric potential of specific things. We're given the idea of electric potential, or in this case, electric potential difference, which we're going to call voltage, and we start analyzing components of circuits using this idea. So if you take the charge divided by the potential, delta V, you get this capacitance. If you look at the units, we have coulombs here on the top, and we have volts. And if you remember up here, you can define volts as joules per coulomb. So it looks like if you define this as joules per coulomb and you have this whole thing divided by coulombs, this looks like it is coulomb squared per joule. I'm not too sure if that's actually the unit, but typically this equation here is used if you want to find the voltage drop across a capacitor. So you could multiply this voltage here and you have this equation CV equals Q. So this Q will be the charge on the capacitor if you're given the voltage across the capacitor and the capacitance itself. Normally they actually give you the capacitance because it's a known circuit element. It's something that's, you can buy in a store and you have a given set of capacitance in farads. This over here is a more fundamental sort of equation. So what we have on the top is epsilon naught, which, remember, is the constant given over here in the physical constant section. It is the permittivity, I believe, of free space. And actually, epsilon naught is the permittivity of a vacuum. So normally this space between capacitor plates is full of nothing, like it's supposed to be a perfect vacuum. Sometimes there's air in here, other times there's another dielectric medium in here which changes the capacitance. And these two things are just metal plates. So this equation here is telling you that the area of the plates, because imagine these plates are like two-dimensional, three-dimensional in reality, but they have some kind of area over here. So this area is going to be given to you, or maybe you have to calculate it if they tell you, hey, we have these two plates, they're placed right next to each other. You are given a length and a height, find the area. This over here is the distance that separates the capacitor plates. So let's say you have a bigger area. The capacitors have bigger plates, or are made of bigger plates. It will create a bigger capacitance. If you have a bigger distance, it will lower the capacitance because it's in the denominator here. If the capacitor plates are closer together, meaning this D is a smaller number, it will increase the capacitance, and this epsilon naught is a constant. So you have these two ways of finding capacitance, or these two ways of finding other parameters if you're given the capacitance. This equation here is the same equation. It is an equation for U, which is potential energy. This is the energy that is stored inside of the capacitor. Normally, they introduce the capacitor as the circuit element that stores electric energy. So over here in the first section on electric potential, you're introduced to electric potential energy. It is defined like this. The capacitor actually holds some electric potential energy inside of itself. And the equation that follows this is you have a Q squared, which is the charge on the capacitor, divided by 2 times its capacitance. So you take this, you work out the units, and you should get joules here. Normally, joules is the unit for energy. And again, remember, if you need it in electron volts, you can convert from joules to electron volts over here. So this equation, if you replace a couple things in here, you can get it written in 2 different formats depending on what's given to you. So let's say a problem asks you to find the potential energy stored in a capacitor. you can take a look at each of these three equations and ask yourself, which one of these parameters do I have? Maybe I have the charge and I can use both of these. Maybe I have the charge and the potential across it. I can use this equation. Maybe I don't have the charge, but I have the capacitance and the potential. Using this equation, you can change both of these equations and get a different form. So if you replace the capacitance here with Q over V, this becomes now Q over delta V. And that delta V goes on the top over here, and one of those Q's cancels with one of these Q's, so you get a Q on top. 1/2 Q delta V. And then the same thing here, you can replace, I guess, the charge Q over here. So if you multiply V on this side, you get CV is equal to Q. Replace this Q into here, and you get V squared over here. So three different ways of looking at the potential energy stored in a capacitor. These two equations are ways to add up capacitors in a circuit. So like I said, this is the capacitor that, I guess, symbol for a capacitor that's used. But most of the time you can line up and create different kinds of circuits. So here we have capacitors in series. So this is in series. This is opposite to, or I guess complementary to, capacitors in parallel. So capacitors in parallel look like this. This is maybe C1. We'll call this guy C2. They are connected by their ends like this. Connected at both ends, you could say. Meanwhile, the series are connected only at one end. This is C4 here. And we could, boom, connect it like that. So this is parallel. And these equations here tell you how to calculate the equivalent capacitance. So in circuit diagrams, you can always combine these things and create one equivalent capacitance. Most of the time you'll have a complicated looking circuit and you want to just reduce everything down to just one equivalent capacitor. And the way you do that in parallel is actually very simple. So let's say we want to find the equivalent capacitance for this parallel circuit. All we do is, as you see over here, we look at the parallel combination. All we have to do is just add up the capacitors like a regular sum. So we take C1, add it to C2, add it to C3, add it to C4. However many are in parallel, make sure they're actually in parallel, right? If there's a resistor here, it's actually in series, I believe, with this one. So the more you work with these little circuits, the more you'll get used to how to add them up. But these ones here are all in parallel. Meanwhile, these ones here are in series. So the equivalent resistance here would just be the sum of all these guys. Meanwhile, if you look at the series combination, it is a little bit different. You get the equivalent capacitance by this 1 over or inverse summation. So 1 over the equivalent capacitance, as shown over here on the left side of the equation, equals the sum of the 1 over each of the capacitances here. So you take 1 over this capacitance, 1 over this capacitance, 1 over this capacitance, add all these guys up together, and then take inverse of all of this to get the equivalent capacitance, right? Because the left side of the equation equals 1 over the equivalent capacitance. If you had a slightly more complicated scenario where you had, for example, 2 resistors here and then maybe a third one in parallel, what I would do here is combine first these two with the series combination. So series combination is right here. So I would do CEQ, let's call this one C3. So this would be 1 over this equals 1 over C1 plus 1 over C2. So I can basically erase all of this and create another capacitor here, which I'll call CEQ, right? And that has a capacitance of, basically, if I erase this and I put, how do I do this here with not destroying my work? too much, I will put these guys here, and I'll put big brackets like this, like that. And now, since these two are in parallel, how I can combine all of this to get the total? So I can make a new circuit down here, which is just C total. This is the combination of all of those original C1, C2, C3 circuits that I showed here. Is I take, I just take this capacitance here and I add C3 to it. So 1 over C1 plus 1 over C2, all of that to the -1 because we want to take the inverse, and then I just add C3. This would give me the total capacitance. And you do the same thing for resistors, except a little bit different. You have kind of opposite equations, which we will get to in a second. And finally, over here, you have the capacitance, CO, if there is a dielectric constant kappa between the capacitor plates. So this is a problem if you have some other medium here. Let's say you fill this with like some plastic material and not air. You're going to get a slightly different capacitance, which is going to look like C nu is equal to kappa Q over delta V, right? I'm just using this equation. I'm taking the old C, multiplying by kappa, and I get the new C. And kappa is normally a constant that's given to you. So now that you have this equation here, you can just multiply by kappa everywhere if you want to find the new capacitance. So I can multiply by kappa here, by kappa here, kappa here. I can multiply kappa everywhere I see a Q just by using this equation here. And over here is a way of finding the same thing as what we saw in this equation, the potential energy stored in a capacitor. If there is a, if the electric field is given to you. So this equation I actually have not seen too much, but if you're given an electric field, I think inside the capacitor, you could take this squared, multiply by epsilon naught, divided by 2, and you should find the energy stored in a capacitor. Yeah, this equation and this equation I haven't seen any problems for, but I will try to find a few in the book, and I'll post a video if I think it is helpful for y'all. So that's fairly simple, capacitors and dielectrics. I kind of went over that fairly quickly. And normally for midterms, the content is focused on this stuff here. So I'm sorry if I breezed by through this thing fairly quick. Maybe I'll do a couple of videos on this section so I can more deeply go through it. But for now, let's continue this video and end it off before the 2-hour mark by going into this resistance and resistivity section. So this equation here is defining electric current, finally. Current, as a function of time, current can change through a resistor, or sorry, through a wire. Let's say we have a wire here. There is charges inside of it. Maybe they're positive charges. Maybe there's electrons, so they're negative charges, but they're all flowing through this wire this direction, kind of like a river. And how you find the current is literally you take a derivative, d, of the charge q as a function of time. So normally this q is a function of time. You take a derivative of this q and you find the current. And this is just the definition of current. Normally you wouldn't use this equation unless they actually give you some kind of charge q, a function of charge, and they tell you find the current from this. And it's also good to know current is defined as charge moving through a wire as a function of time. So what we have here is, I believe, current density. So we have current density going through a wire. If you can imagine a wire like this, and it has some current going through it, current I, and the area over here of this wire is A. So if you have current over area, you get the charge density, sorry, not the charge density, but the current density, which they use a letter J for it. Sometimes current and current density is used interchangeably. They are different things, so just keep in mind I is normally used for current, and J here we use for current density, area. Over here next to current density, you see another equation that's very important, and there's a couple of symbols in here. So I'm going to list out all these symbols to make you guys see kind of a different picture of current. So here we have N. N is the number of charge carriers. So this is normally electrons. Here actually they give you a Q. So this is the charge of the charge carriers. So if you have a positively charged current, this Q would be positive. If you have a current of negative charges like electrons, it will be negative. And over here, this VD is an entire thing written together. It is called the drift velocity of the charge carriers. So if you have a certain number of charges, a specific charge, and a specific speed that they're going through, you get the charge density. And if you multiply that by the area over here, then you get current. So current is literally N, the number of electrons, if they're electrons, E, which is the charge of the electron, or if you want to be more general, you could do Q, which is the charge of whatever the current is made of. It could be a current of protons, doesn't matter. Here we have VD, which is the drift velocity, how fast the electrons are moving through there. And then A, the cross-sectional area of the wire that the charge is going through. So maybe you have all of these charges here. This is N. They are positively charged like this, and they have some drift velocity, VD. And this over here is the area of the wire. So very important equation. If they ask you find the number of electrons passing through a given area, the number of electrons is here, the charge of the electrons is here. Normally they should give you the current. Sometimes they make you use Ohm's law, which is Ohm's law even here? We'll get to that in a second. But yeah, very important equation. And also that is where this equation here, or this physical constant, the speed of light, might come in. Because sometimes they say, oh, electrons are moving through this wire at the speed of light. Calculate the current if there's this many electrons, or some question like that. So that is current and current density. Here we have an interesting equation. This is actually a super fundamental equation, and it tells you that the current density J is equal to sigma, which is actually a new definition. It is not the same sigma as the one I told you guys about over here. This is surface charge density. And sigma over here is used to mean something different. It is actually called the conductivity. So very, very sorry, conductivity. Here it is, where the constant of proportionality, sigma, is called the conductivity of the conductor. Materials that obey equation 26.6 are said to follow Ohm's law, named after George Simon Ohm. More specifically, Ohm's law states the following. For many materials, including most metals, the ratio of the current density to the electric field is a constant, sigma, that is independent of the electric field producing the current. Very, very interesting. So yes, this thing is the conductivity of the material, and you multiply it by the electric field. So what this equation over here is telling you is if you apply an electric field over some wire with conductivity sigma, this conductivity is normally given to you, it's a property of the material, then you get a current density that is proportional to the electric field. Proportional just means that this thing has an equal sign with this thing on the other side, and there's just a proportionality factor sigma here. So if materials follow this thing, they are said to obey Ohm's law. Now here is actually Ohm's law. It's normally written in another form, which I will write right here. It is written as V is equal to IR. the potential over a resistor of resistance R is equal to the resistance times the current going through that resistance. So here we can attach a voltmeter. This is the voltmeter. And we have a current I going through it. If we have the resistance, which is another circuit element that I haven't really introduced yet, like formally, I'm just talking about the equations. It is literally just a piece of metal or something else that slows down the flow of electrons. So if you remember over here, we talked about current and current density. This current is flowing through here maybe smoothly, and then it gets to the resistor, and it's kind of like a rocky path. It kind of slows down the current and pushes it out of here. So there's a voltage drop across this thing. So the voltage here drops a little bit. And you can use Ohm's law over here. If the material obeys Ohm's law, if the material is ohmic, as you saw in the book, you can use Ohm's law to figure out things like the current going through a resistor if you know the voltage. If you have the voltage across the resistor, you can find the current. If you have the current and the voltage, but you don't have the resistor, you can reverse engineer and calculate the resistance. Cool. I'm going to erase all this here, and I'm just going to quickly tell you about another thing, which is this equation here. So this rho and this sigma are Greek letters that are used a lot, but I just told you that rho is the conductivity. If you take 1 over the conductivity, you get rho, which is the resistivity. They're inversely proportional. What that means is it's kind of like a percentage. So if you look at this equation, rho equals 1 over sigma, the bigger rho is you take 1 divided by a really big number, the smaller rho becomes. Makes sense? So the more conductivity a material has, the less resistivity it has. And the more resistivity it has, the less conductivity. Inverse relationship. If you want, you can multiply by rho on this side, and you can you can multiply by sigma on this side and divide by rho on this side, and you can get another equation, which is sigma is equal to 1 over rho, the resistivity. It just tells you that conductivity of a material and resistivity of a material, which literally means what it sounds like it means. Conductivity is how likely or how good of a conductor a material is, and resistivity is how good of a resistor a material is. So normally metals and stuff have really high sigma, really high conductivity, and really low resistivity. They're linked quantities. It's like I can't really think of a good example right now. Let me think. Okay, I got one. It's like the more water you drink, the less thirsty you are, and the more thirsty you are, the less water you drink. Is that a good analogy? Hopefully that makes sense. This is just an equation telling you that. So if you're given the resistivity of a material, you can find the conductivity. If you're given the conductivity, you can find the resistivity. Again, not really useful, except for when it's actually used in equations, and it's useful to know what it means, right? Now, this equation here is another way of writing the resistance of a material. So the resistivity, like I said, is a thing that tells you how good of a resistor a material is. Here, you can actually find the resistance, which normally is written in these units ohms. And what that is literally, they have the resistivity here, which is, it has its own units. I'm not too sure what it is. Okay, here's actually a table of some common materials and their resistivity. And you can also find inversely their conductivity. So silver, as you can see, has a really small resistivity. The resistivity has units of ohms times meters. And the reason that's the case is because of the equation that we saw earlier. This one here of resistance equals rho times the length of the material divided by the area of the material. Normally it's a wire. That's why they use that equation there. So silver is a really good conductor, meaning its resistivity is really low. You can see 1.59 times 10 to the negative 8. Meanwhile, quartz has really high resistivity, 75 times 10 to the 16. Cool. So I'm going to go back here and tell you guys again, the resistance over here of a wire, you can find it if you are given the length, L, over here the cross-sectional area, A, and the resistivity of the material, which is a property of the material. Maybe it's copper, and copper will have its own thing. So you multiply these numbers together and you get the resistance. This is actually something you do in a standard E&M lab. So I hope that was helpful to take a look at. Now we are going to get to this equation here. Is actually pretty interesting. It's the same sort of equation they gave us here, except they replace VD with QE over ME and then tau. So where have you guys seen this before? If you plug these numbers in for VD, you get the same equation here. So where have you guys seen this equation? Can you think of it? Let's go back to the first section here. And let's see here, we have acceleration, which is Q times E over M. And if M is the electron, you do ME. If Q is the charge of the electron, normally it's QE or just E. But yeah, that gives us the acceleration due to the electric field. Very cool. And what's very cool about that is, here we have the acceleration. So this, you could say, is the acceleration. And here we have t, which normally is a unit of time. How long does it take for you to accelerate this electron? So if you multiply a times t, you get velocity, drift velocity. So basically what this equation here is telling you, this one is current density if you replace the drift velocity by the electric field acting on the conductor, multiplied by how long you're running the experiment for. Let's say you connect some battery and create an electric field across your conductor. You have the charges here, which you have a squared on because of this manipulation we did with the VD. And you have the mass of the charge carriers, which in this case is the electrons. And you run this electric field for a certain amount of time. You can get the current density with this equation here. So that I just got by plugging in some previous sort of equation that we saw from there. And the reason I saw it is because this QE over M looks very familiar to me if this was just a 1 over here instead of a squared. Nice. Now we're going to get to the final sort of things, which is the power due to a battery with a resistor on it. So here you have two different ways of writing power. It is current times voltage. So if you have some circuit or something, or a battery that is outputting a certain amount of current and voltage, you can multiply these two things together and you can get the power output. You can also, if you use Ohm's law, so remember here we have V equals IR, you can replace V with IR. The I becomes squared now because we have two of them, and we have the R now. So two different ways of writing power output. Either you have the current and the resistance of the power source or the circuit you're looking at, or you have the current and the voltage. And here is another way of rewriting it. So if you take the first equation, P is equal to IV, you can use V equals IR, calculate from this by dividing R on both sides. This is I, by the way. And you get I equals V over R, and you can replace I into here, which should give you V squared over R. So three different ways of calculating power output here, depending on what you have. And again, it's kind of like a trigonometry. If you have two sides of a triangle, you can always calculate the third. So normally you should be given either the current or the voltage, or the current or the resistance, or the third case, the resistance and the voltage, and you should be able to find the power. So that covers the section on resistance and resistivity. Again, I haven't done any problems here. Remember also what I said by talking to you about this. Here, rho and sigma are conductivity and resistivity. Here, sigma is charge density. So please just remember that. And now we will complete the section by going into this part of the chapter, which is actually a small part, but very dense. So these two things here, what are they? They are Kirchhoff's rules. Okay, that's what I was looking at. Kirchhoff's. Is it one F or two F's? Kirchhoff's rules. So these are two rules of a circuit. Let's say you had a complicated looking circuit with multiple loops. So here is a charge element, or an element of the circuit. It is a battery. Here we have a resistor. Here we have another resistor. Here we have a battery. And here we have another resistor. Kirchhoff rules are two rules that always apply to any function like this. The first one is telling you the sum of all currents going into a junction is equal to 0. And the second rule is telling you the sum of all voltages or voltage changes over all closed loops is equal to 0. So what is this first rule telling you? We'll take a look at this this circuit. This battery here has a positive and negative end and a positive and negative end. So they're going to be creating some current. Let's say the current is going this way. Let's call this I1. Over here at this junction, the current now is going to split into I2 and I3, right? Over here, I3 will come and again recombine into the same current, I1, and over here, I2 will go all the way around this and combine. So the junctions, which are the points over here and over here, the big red spots, this is what the first equation is telling you around. The sum, the addition of all currents I over a junction or in a junction is equal to 0. So from that, you can create this equation here. Let's look at this junction over here, junction. I can see that current 2 and current 3 combine, I2 plus I3, and they equate I1. That's the same thing as what is happening in this junction. I have current I1, which splits and creates I2 plus I3. Now, I haven't really talked about circuits on this channel, but what you can say in a circuit is currents leaving a node and entering a node have a specific sign. So if we assign currents leaving a node, so let's say we're looking at this node. The only current leaving a node is this one, I1. So let's call this negative since it's leaving the node. And these two are entering the node. They're going inside of it. So let's call them positive, right? That is this equation here. So I technically already did that by creating this equation. That's why I like creating this equation. I look at it as rivers. This guy combines with this guy and creates this guy. So I3 combines with I2 to create I1. Or you could say I1 is leaving the node. It is flowing away from the node. Therefore, it will have a minus sign. I3 is going into the node and I2 is going into the node. Therefore, they're positive. You should get this equation here, but let's say you take this I1 and subtract it on both sides. What you should get is minus I1 plus I2 is equal to 0. That is what Kirchhoff's first rule is telling you. It's telling you the sum, here I'm going to write it right here. The sum of all currents across a junction is equal to 0. So what I did here is I said, okay, the sum. This one is negative because it's leaving the node. these two are positive because they're entering the node. The sum of all of these equals 0. Or an equivalent way of writing this is, as you saw, I can take this I1 and move it on this side, and it'll become positive. So you can rewrite this equation as I2 plus I3. So these two currents going into the node combine, and they create I1. Similarly, on the other side of the thing, we have the same sort of equation. I1 splits, and it creates I2 and I3. If we use the same thing, currents entering a node are negative. Currents leaving the node are negative. This thing is negative, and this thing is negative. So we have negative I2, negative I3, and I1 is entering the node, so we have plus I1 equals 0. This is literally me using Kirchhoff's first loop rule, and I create this equation here. I don't really like these minus signs, so I'm going to add I2 on both sides and basically move them to this side of the equation, which will get me back to this original equation. So that is how you can see this loop rule first. The second loop rule is a little bit more complicated, and it talks about voltage drops. So here you have a change in voltage, and here you have the word closed loop. So if you take a look at the circuit here, let's say we keep all of those currents. We can create two loops. Let's choose this loop as loop 1 and this loop as loop 2. These are arbitrary loops. I could have chosen them to go the other way. I could have chosen them to go like this, but they are loops around the circuit like that. So this second equation is telling you the sum of all the change in potential over a closed loop equals 0. So what this is telling you is, let's say we start the loop here and I'm doing loop 1. I'm going to go along the loop like this, boom, 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 until I get to the first charge element. In this case, it is a resistor. Let's give this resistor a name. We're going to call this resistor R1, this one R2, this one R3, and we're going to call this battery epsilon. Normally they use this for electromotive force, which again I haven't talked about in this video, but there's only so much I can cover in an equation sheet. So this loop, it will create another series of equations. And how you can draw that is, let's say we're looking at loop 1. I'm going to start right over here at this point, at this node. You can start anywhere, but wherever you start, you have to go around the loop and end off at the same point, because that creates a closed loop. I can also do the same for loop 2. I could do this. I could have chosen this loop if I wanted to, but it has to be a closed loop. So technically, I can only choose 3 closed loops. This one, or this one. In a bigger circuit, if the circuit continued here with a lot of other branches like this, then you have many loops to go through. But in this case, you just have these 3, 1, 2, and 3. So let's choose loop 1. We're going to start at this node. We're going to go around here, around here, around here, and then around here. And we're going to look at each element of the circuit. First, we pass through resistor 1. Then we pass through, resistor 2. And then we pass through resistor 1. And then we pass through the battery. And then over here, there's nothing in the circuit. So what this equation looks like is, well, we have a 0. So I like to start with the 0. I'm going to do 0 equals, or you could do equals 0, whatever. You can put the 0 on either side of the equation. And I'm going to start and go along the resistor. And I'm going to see that the first element I see is R2. Now, what I'm looking for is actually the voltage drop across this resistor. So I'm going to multiply by I, and the current that is going across resistor 2 is I3. This is just how I labeled the diagram. I'm going to do another video on Kirchhoff laws to go a bit more in depth. But yeah, we have that, and I am looking here at the direction of the current, which I also chose. I said it was going this direction, and the direction of the loop. If the direction of the current and the direction of the loop are going in the same direction, this is going to be a voltage drop. So I'm going to have a minus sign there because it's asking you for the change in voltage. How do you know this? Just be patient. Take a look at my Kirchhoff loop rule video, which I will post sometime shortly, or take a look at some other YouTube videos. Search up Kirchhoff loop rules practice problem, and you should see their technique of doing it. So at this stage, I have drawn this over here, and I'm done, and I'm going to move past this resistor to resistor R1. So here I will write R1, and I'm going to multiply by the current going across it, which is I1, because I want to have voltage drops here. Remember, this is a change in voltage. Sorry, not voltage drops. I just want to have a change in voltage. And the way you get voltage is with this equation here. You have V equals IR, Ohm's law. So I'm using that equation. I'm multiplying a resistance by a current, and I'm getting a voltage out of it. That is what Kirchhoff's second loop rule is talking about. You have a voltage here. So I'm looking now again at the direction of the current. So the current is going this way, and my loop is going the same way. This will again be a voltage drop, so a negative sign. Now I am done with this second resistor, R2, and I'm going to the battery. And the way I see the battery is I'm going to look at the direction of my loop. My loop is going in this direction, and I'm going from the negative side to the positive side. It's kind of like I'm going up these stairs. This is going to be a voltage increase, so a positive sign. If my loop was going the other way, like for example, I chose my loop to go this way for L1 instead of this way, then I would be going down this little ladder of positive and negative, and it would be a voltage decrease with a negative sign there. Similarly, these things here, they would not have negative signs, they would have positive signs. That's going to be something I talk about in the longer video of Kirchhoff loop rules. So now we can take a look at the final thing of this circuit. Like I said, it's a positive, and we put a epsilon naught or epsilon 1 because that is the voltage of the battery, which should be given to you. And now this equation is complete. So that is one of the closed loops for Kirchhoff's second law, the voltage drops in a closed loop. As you saw, we started at one point, we went across the circuit in a closed loop like this, and we just added up the voltages at each element of the circuit. Over here we had a resistor, it had a resistance of 2, we had a current going through it, and it is a voltage drop. The way I remember that is because the current and the loop are going in the same direction. If my loop was chosen to go this way, the current and the loop are going in opposite ways, so that would be a voltage increase. And in these scenarios, I would have positive signs. So we did this loop. Now let's start at the same point here and do this loop. Right? You could start at any point. Actually, you know what? For funsies, let's start at this point. Just remember we start here. We're going to go here. This branch has nothing in it, so we have nothing to worry about. We're going to go here. This is the first element we reach. We finish with that. We're going to go here. This is the second element we reach. We finish that. We go here. This is the third and final element, and then we get to our starting point, which closes the loop. So we're going to start at this point, and we're going to reach resistor 2 first. Again, I'm following the loop direction that I've chosen. So this time, I'm not going to put the equals 0 here. I'm going to do it here, equals 0, just to show you that you could do this in any way you want. I'm going to label this loop 2. And like I said, we reach R2 first. I'm going to multiply that by I3 because that is the current going through it. And in this case, I have the loop going this direction. So it is going this direction. This is the loop, while the current is going this direction. If they're going in opposite directions, this is a voltage increase. So I'm going to actually have a positive sign here. Okay? Don't worry about this. You're going to get used to it when you work on more problems. But now we are done with this. As you saw, for the first case, we had a minus sign there. It's a voltage drop. For the second case, we had a voltage increase, a voltage gain, just depending on the current direction and the loop direction. Now we are done with this element. Let's move on to the second one. Again, remember, our loop is going this way. Here, we're going from the positive to the negative, so I see it as follow the loop direction. We get to here, and we are going down these stairs, voltage decrease, from the positive to the negative, from positive to negative, going down these little stairs of the battery. So that will be a voltage drop minus, and we put the voltage of the battery, epsilon 2, which is given to you. We have completed this circuit element, and we're going to continue with our loop, and now we get to the third and final loop element, which is R3. So I'm going to do R3 right here, and I will multiply it by I2, which is the current going through this, I2. And let's take a look at which direction the current is going. So the current is going this direction, and it is going in the same direction as my loop. If they're going in the same direction, it is going to be a voltage decrease, so a minus sign. So I'm going to put a minus sign right here, and that completes all of our equations. Now look at this. We have this equation, and I'm going to copy them right here. Paste. I'm going to erase this, erase this positive sign, it doesn't matter, it's at the front of the equation. I'm going to move this 0 on the other side so we have both the equations looking the same. And I'm going to set them up like this, right? You can manipulate these however you want. And we have this equation, which is from our first Kirchhoff loop rule. Paste. So Kirchhoff's laws are basically laws that make you figure out 3 equations like this. 1, 2, and 3, right? You always get 1 equation per junction. So here we had 1 junction, and here we had another junction, but it told us the same equation, right? This equation and this equation, they're the same. That's from the first Kirchhoff law. From the second Kirchhoff law, we got 2 equations, 1 per loop. So you can see here we had 1 loop, here we had another loop. If you want, you can find this loop as well, but I don't think it will be too helpful. Maybe it will be. You can calculate it on your own if you want. You can maybe do a big loop like this, right? Call that loop 3. You can start here and just do the same addition that I did. First element, second element, third element, fourth element, and then finish up here. You're going to be missing this middle branch, but it's okay. In this case, you were missing this whole outer branch, and in this case, you were missing this whole outer branch. So just make sure your loop is closed as shown over here in Kirchhoff's second law, and you should get 1 equation per loop like this. Yeah. Hello. Okay. So the point of Kirchhoff's loop rules is here you have 3 unknowns. You don't know these currents. And if you have 3 equations, you can use a system of equations to solve for the 3 unknowns. Typically, Kirchhoff's loop rules are given to you in a circuit where you know the resistances. So R1, R2, and R3 are known, they're given to you. And you know the battery voltages, so these are also given to you. But you don't know the direction or the magnitude of any of these currents. So in the beginning of the problem, I guessed these currents. I didn't actually know what they were. So here I have 3 equations that if I solve, I will be able to actually find what I1 is equal to. Maybe this is 3 amps. I will find what I2 and I3 are equal to. And I will also know if the directions that I chose here will be correct. So this is a very long explanation. I don't want to make this video too long. It's already very long with 2 hours. So I'm going to erase this, and I hope that explains these 2 laws over here. Now we're going to get to the final thing, which is RC circuits. Okay, I'm going to very, very quickly go through this. Let's say we have a battery like this. This is epsilon 1, and then it is connected to a capacitor. Let's call this C1. And it is also connected to a resistor, okay? And over here, we have a switch, which we can open and close. If the switch is open, the charge on this capacitor will be, I think 0, right? Because there's no voltage on the capacitor. So these RC circuits are circuits that change their behavior. They basically are called charging and discharging circuits because of the capacitor. They're dynamic circuits, you could say. They're not passive circuits. Maybe you can think about it as a battery and a resistor connected like this. Nothing really happens. You apply a voltage, maybe the voltage of the battery, to this resistor, right? You can find the voltage here dropping across this resistor, and nothing really happens. The resistor heats up. That's pretty much it. But this capacitor, once you include it, it starts changing the dynamics of the circuit a little bit. It gets charged through a given equation, which is the equation over here, and it gets discharged through a given equation. And it happens through this time constant thing right here. So this time constant is the resistance times the capacitance of the circuit. So let's say here we have R1 and C1. The time constant is literally R1 times C1, right? If you had a bunch of resistors or capacitors in here, you have to combine them using the rules that we had before. And by the way, this equation sheet here, it does not give you the series and parallel combination of resistors. They are literally identical to these equations, except you flip these. So if you have resistors in series, you use this equation. And if you have resistors in parallel, you use this equation. A little bit of a thing to keep in mind because it's not on the equation sheet. So these equations over here, they tell you the charge as a function of time on the capacitor in the RC circuit. And this equation also tells you the charge as a function of time of an RC circuit. So what do these equations look like? Well, here you have an exponential, and it has a t in the exponent divided by an RC. Over here you can see RC is the time constant tau. So sometimes you'll actually see these equations written as, let's say I take this one here, and what that looks like is Q e to the minus t over tau, where tau is this constant. You can also have this other equation, Q1 minus e to the minus t over tau. So these are the two equations given here. Here is one of them, and here is the other one. And over here, they just replace this Q with a C times epsilon, where epsilon is the voltage on the capacitor. Remember, if you look at this equation here, you can have CV is equal to Q. In this case, they just replace V with this epsilon. So you can replace this Q in the equation with CV, where V is the voltage of the battery, and it's written in this epsilon, electromotive force or whatever. So yeah, this equation here is the same as this equation, and these two equations are the important ones, the ones that I've written right here. They're the charge and discharge equations of the capacitor. This final equation here is literally just a, I think it's exactly this thing here. So you have the epsilon, which is, you can replace it with delta V. It's literally just the voltage of the battery. And you have U, which is the potential energy stored in the capacitor due to the battery. So here you have 1/2 Q times epsilon, or you can replace epsilon with delta V again. Here in the top, you have 1/2 Q and then delta V, which you can replace with this. The same equation down here. I don't know why it's given twice. I guess just, to tell you this is for RC circuits and this is just for capacitors on its own. And then on the other side, you have, two different ways of writing potential energy in a capacitor, you have 1/2 C and then epsilon squared. Here you have 1/2 C and voltage squared. You just replace voltage with epsilon, or here you replace epsilon with the voltage. Okay, so one final thing I'm going to show you is the behavior of these two circuits. Okay, so here's the first equation. I have y equals q right here. I have q as a slider, times the exponent e to the power of negative x. Here x is the function on the x-axis, which in the actual equation, in the equation sheet, they have x as t. And on the bottom I have t, which is actually the time constant tau. So I hope that makes sense. And as you can see, this slider here is basically bringing up q, where the function intersects the y-axis. So you can see here that little gray dot is, if I bring it up to 10, the intersection with the y-axis is 10. If I bring it down to 1, it intersects at 1. If I bring it down to 2, it intersects at 2. Let's keep it at 5, okay? So that q, the q that is multiplied in front of the epsilon, is literally the total charge of the capacitor. This is the discharge circuit. So this is the function, this is the charge on the capacitor as it's discharging. And you can see if I change tau, the time constant, you could see that the function either grows its slope or makes its slope much steeper. So if the time constant is a super small number like 0.1, it means the capacitor discharges very fast. If the time constant is very big, like let's say 10, the capacitor takes a long time to discharge. All right, I hope that makes sense. I'm going to leave that function here, and I'm going to write this new one. So I have this new function here, and I have the same variables. As you can see, if I increase the charge, it reaches an asymptote at that number. So you could see here the function kind of reaches a maximum and then hits 10. If I lower this, it will reach a maximum at another number. Here's 0. Let's bring it up to 5 again, right? And oops, this is 4.8. Let's go to 5 exactly. So let's say q is equal to 5. This function that I have, the purple one right here, is y is equal to q, open brackets, 1 minus that exponent thing. The same thing, except q is now outside of the brackets and there's a 1 minus. This is the charging function. If I zoom in here, and let me just take this axis and grow it like this, you can see we reach a maximum at q is equal to 5. So 5 on the y-axis, you can see if I go all the way here, the purple line is pretty much touching 5 exactly, right? So what this is saying is after a long time, remember time is on the x-axis. After a long time, the capacitor is fully charged and it reaches the maximum charge, which in this case is 5. So that's why they use the letter Q in the front. Now, if I change the time constant, so I make it much smaller, the capacitor takes a very short amount of time to fully charge. You can see here, it takes, I don't know, a couple of seconds. It's pretty much reached the top after x is equal to 2. At x is equal to 2, it's pretty much already at 5. You can see the 5 line over there on the y-axis, and you can see it's pretty much already touching, right? That's if I have a small time constant, t. But if I increase the time constant to 10, you can see now it takes a long time. It takes all the way to 40 seconds, for example, to reach the same amount. So let's go back to these equations. Basically, these equations here, these ones, are the charge and let me actually write this in here. Charge and discharge functions of the RC circuit. So if you have a circuit like this, you have the time constant. The time constant is R times C. So if you multiply these together and you get a very small number, as you saw, 0.1, the time constant will be very small, and you will have a very quick charging or a very quick discharging. You could see the functions here are related, the charge and discharge. The red function is the discharge because the capacitor is losing charge. Remember, these equations are literally equations for charge Q as a function of time. So here what I'm plotting on the y-axis is charge, and what I'm plotting on the x-axis is time. Charge is y, time is x. I'm plotting this. Here we have the charge function. So this is charge, this is discharge, right? Boom. So okay guys, I'm gonna stop the video here because I talked a lot, but basically I talked about pretty much every equation here. If you think anything here is confusing, that should be a sign to just quickly look over what I said. I know I may have said kind of some strange things in this video, some parts about the resistance and capacitor section that are I guess maybe make you feel a bit uncomfortable. That is a sign to study a little bit if you have an exam like this coming up. And yeah, let me know, drop a comment if you have any questions about this. Sorry again for making the videos very long. I appreciate you guys for listening. Thank you. Enjoy the day. Peace.